As math and science teachers, we strive to provide experiences which focus on the content standards, connect the content to real-world experiences, integrate engineering design, give students voice and control, engage students with hands-on experiences, connect to a societal need. CBL integrates all of these characteristics as students begin with the big idea, develop an essential question, identify a design challenge, brainstorm guiding questions, participate in concept foundation activities, and utilize the engineering design process to create and test design products. Now, let's look at these pieces and how they fit together.
Academic standards. Challenge-based learning units must meet the needs of the state and national academic standards for math and science. Hook. The hook is designed to catch the attention of the students and help make the challenge relevant to their lives. It could be an activity, a video, or teacher presentation. The hook precedes the big idea.
This cello is made from an oil can and wood that was thrown away in the garbage. It sounds like this.
This unit covers transformations, which is a math expectation for 8th graders. Using geocaching as a hook, the challenge requires students to make a coordinate grid using reflections, rotations, and dilations of a polygon to map locations. The hook involved students using their own cell phone devices. They navigated around the school using a GPS on their smartphones to various places on campus where I hid virtual treasure. This was their introduction to geocaching, and you could feel the excitement and the longing to know more.
Big idea. A big idea is one that is important on a local or global scale and that students can work with to gain the deep multidisciplinary content knowledge and understanding that is required by the standards for their grade level. An example of a local big idea would be improving classroom design, and a global example would be sustainability of the environment. What is sound?
The big idea, which was tracking, locating, and investigating locations.
Essential question. The big idea allows for the generation of a wide variety of essential questions that reflect the interests of the students and the needs of their community. Each group will narrow their thoughts to one essential question. The essential question: how is the musical scale created? We generated interest by looking at a wave generator, and then mathematically we tied the unit circle into the sine wave and the cosine wave. Challenge. From the essential question, multiple challenges are brainstormed by students from which one is identified, or the teacher presents the challenge, bypassing the student brainstorm. This concise challenge asks students to create a specific solution that will result in concrete, meaningful action. The challenge utilizes the engineering design process that answers the essential question. First began by studying various types of musical instruments and how they generate sound. Students then broke into groups and studied various musical instruments and how they produce sound. Then we set about constructing our instruments, keeping in mind that we had to produce an 8-note scale.
It's time to come up with a project, and you guys are going to help me do that. But before we can just say, hey, this is what we want our project to be, we need to have some conversations, okay? So we're going to do a lot of discussing today, and by the end of the day, you guys are going to have given me a lot of ideas so that this weekend I can go home and I can use all of your ideas, put them together, and come up with one big challenge, which is going to be a project for you guys to complete next week.
House arrest animals.
Yeah.
Chase King.
That's definitely. What, he has house arrest?
You didn't know that?
No. Right now?
Yeah.
Wow.
This is technically the only thing that's allowed to be out.
I haven't.
Yeah, some kid was messing with
So house arrest is a way to, like, you know, make sure that people that aren't supposed to be out and about are actually where they're supposed to be. What are you guys thinking over here? What's a good one you've come up with?
Oh, lost phones.
Yeah. Let's talk, though. I want you guys to choose one out of all of yours that we're going to talk about in class here for just a second.
How I track down animals that are in trouble in the northern part.
Her idea, if you didn't hear her, was to track different animals. Perhaps you were saying specifically polar bears, right? And you were talking about global warming and kind of just to see, are there a lack of polar bears out there because of the warming conditions? Anybody think of that? I know a couple of you said to locate animals. How many people thought of that in their groups? A couple different groups? Good. I think that's a fantastic idea. It's definitely impacting society. Absolutely. This is the brainstorming process. First, we're going to help each other, you know, brainstorm some possible ideas, okay? And then I'm going to go home. I'm going to plan out what it is. I'm going to use some of your ideas here. For example, will GPS help us find our cars? Will GPS help us find iPhones? So I'm going to calculate everything, and I'm going to come up with a challenge. And this is called challenge-based learning. So that means that you guys as a class came up with a challenge. I didn't as your teacher. Okay, I'm just putting it together for you. So I hope it's something good, and then I'll let you know. And actually, though, I'm going to also ask the other classes too. So out of all the classes, we'll kind of figure out what it is that we want to do.
Guiding questions. Generated by the students, guiding questions represent the knowledge needed to successfully develop a solution for the challenge. For example, if the big idea is water, guiding questions might include, how do we use water? How much water do we use? How much is water wasted? How much water is wasted? Can water be conserved? And where does water come from? Preliminary investigations to answer guiding questions. Physical versus chemical properties lab. What is the difference between a physical and a chemical property? Can anything about a material be changed without a chemical change occurring? How are materials that can't be recycled separated from recyclables? How can contaminants be removed without changing the recyclable materials? How could a material's physical characteristics like density be used to identify different materials? Can density be used to separate materials without touching them? In what ways are recyclable metals the same and different from each other? In what ways are recyclable plastics the same and different from each other? In what ways are recyclable paper products the same and different from each other? The EDP segment follows this. This is a diagram of the engineering design process. The first step is to identify and define the issue presented by the challenge. Design a process that will separate a mixture of recyclable materials by their physical properties without manual sorting. The next step is to gather information. This requires research from the internet, speaking with experts, and may involve preliminary tests like measuring water quality parameters or stresses on a building element. Preliminary investigations to answer guiding questions. Physical versus chemical properties lab. What is the difference between a physical and a chemical property? Can anything about a material be changed without a chemical change occurring? How are materials that can't be recycled separated from recyclables? How can contaminants be removed without changing the recyclable materials? How could a material's physical characteristics, like density, be used to identify different materials? Can density be used to separate materials without touching them? In what ways are recyclable metals the same and different from each other? In what ways are recyclable plastics the same and different from each other? In what ways are recyclable paper products the same and different from each other? The next step is to identify alternatives to solve the issue or need. These could be processes or products. Next, students select a solution which best answers the issue or need. Design challenge. Brainstorm separation procedures. Then select the best solution. Then students implement the solution. Next, students evaluate the solution to determine its suitability to meet the need. Test procedures. Preliminary tests show some ideas work well, some ideas show promise, and some just don't work at all. The cycle continues by refining the solutions to improve results. This may require revisiting the steps in the cycle. As this process unfolds, it is essential to communicate within the team and with all stakeholders, for example, teachers and clients. The refined procedures are more efficient, more effective, less messy. Good ideas are adopted by other groups, and recyclables are successfully sorted by their physical property. When complete, students communicate the solution to all stakeholders. Student teams present their results to the teacher, other students, and sometimes to community stakeholders. Student teams presenting their results.